Hi everyone, in this presentation we are going to be taking a look at the theory behind the BERT model. Right, so BERT stands for bidirectional encoder representation from transformers. It is a transformer model that builds on the initial ideas from this paper over here. Right, its attention is all you need, and it's a 2017 paper. It's designed to learn powerful methods of encoding representations from natural language, or in fact many forms of like just sequences of letters, and it has demonstrated state-of-the-art results on many different natural language processing problems in a variety of languages, and even in domains such as scientific papers and like protein sequences. A key insight from the BERT paper is that we are able to use this singular architecture, right? So this is the transformer architecture, and simply do pre-training on a large corpus. So this could be something like what the BERT paper actually used, which is a very large text corpus called the book corpus, which consists of many documents, including Wikipedia. And then through this self-supervised pre-training process, we learn a model that's able to capture very rich representations of text. And then we do not need to modify the model. We're able to take that same model with the same architecture and what we call the pre-trained weights, and then immediately use transfer learning to use it in the task of fine-tuning on another task-specific corpus. So the purpose of this fine-tuning step is to take the pre-trained model, which has already learned rich representations of text, and then continue to train, right? So we call this fine-tuning. Train the model to be able to do a specific task. For example, question answering. This concept is called transfer learning, and is very common in computer vision, but it's only with the advent of the BERT model that's able to use transfer learning in order to achieve state-of-the-art performance. Were people convinced that we could do transfer learning in NLP, right? So that was the key insight from the BERT paper, that we are able to take a singular architecture, pre-train it once on a large data set, and then use transfer learning to fine-tune the model on specific tasks. So this made natural language processing a lot more accessible because people no longer needed to develop specific models for different tasks, and we can just use this singular transformer model. So this insight actually changed the NLP landscape quite a lot. So before we continue, let me just talk a bit more about this pre-training. So in the previous slide over here, we talked about pre-training, right? So what is pre-training? Pre-training is essentially a self-supervised process where we do not need a human to generate additional labels. The label is actually automatically generated from the data. For example, in the BERT pre-training, we use this masked language model sort of task. It's also known as the closed task. So what we actually do is that we delete a few words from the input sequence. For example, there's a word here that's missing and a word here that's missing. And what we do is we use the missing word as the label, and then we train the model to be able to predict the label, which is the missing word. In addition, BERT was actually also trained to do another task, which is this next sentence prediction. Although this is actually not very effective, and in later versions of the BERT model, this particular objective is removed entirely, right? So the key takeaway over here is that we train BERT using this pre-training, which involves this infilling task over here. Let's take a deep dive into the transformer architecture itself, as it will help us understand BERT a lot better. So if you go and like do a Google search for the transformer architecture, you will see this diagram come up quite often. This is the original diagram that was in the Attention is All You Need paper that first proposed the transformer architecture. This diagram is a little bit complex, and there's a lot of components inside. So what we'll be doing through the next like half an hour or so is we're going to be taking a closer look at what are the different components that make up the transformer architecture and why it's so powerful. Alright, so now let's just focus on this main diagram over here. We first realize is that this is actually an encoder-decoder model. So this model is actually split into two components, right? The column over here on the left is the encoder, and the column here on the right is actually the decoder. Right? So if we were to zoom out and look at it from a very high level point of view, we have some sort of input representation, right, going into the encoder, which transforms it into a sort of latent representation, which is then decoded, and then we get output representation. So why is the original transformer designed in such a way? This is because the original model was designed for machine translation. So we actually have one input here, which is the original sentence in the source language. Perhaps this is an English sentence, right? And then after that, we have a output, which we want to be the, say, the next character in the translation into French, right? And then we also have another input. So this input is actually the translated sentence that has been generated so far. So if this was the first step in generating the translation, this would actually be a special start token. And what will happen is that we will feed in the entire English sentence, and then we feed in the first token of the translation, and then we get the model to generate the next token of the translation. So this is how the transformer was first used, and this is why we have this sort of encoder-decoder architecture. The key here is that we want to be able to learn a good latent representation. So in the case of machine translation, we want to learn the sort of meaning inside the English sentence, which is input to the encoder, and the decoder would basically take this meaning and then decode it into the French text, for example. Simplifying the original diagram, we get something like this, right? So we have the input sequence that goes through a sequential um, order of these blocks. So each of these blocks are identical blocks, right? We can also think of this as the transformer layer itself. And in the final encoder block over here, the output is the context vector, which is then passed individually into every one of these decoder blocks. So these decoder blocks perform the role of decoding, and they are a bit different from the encoder block in the sense that they actually have two different inputs. The first one is the sequence input, right? And the second one is basically the context vector that is the input from, the output from the encoder block itself. And the very last encoder block would produce the representation that is converted into the output sequence. Before we continue and look at what's inside the different blocks, let's talk a bit more about the input into the transformer layer itself, right? So that's this part over here. The input into the transformer layer itself is not really that straightforward, right? So let's break it down a little bit. The first thing that I want to talk about are these token representations. So you can see over here that our token representation is basically just a series of these token embeddings. So these token embeddings are very similar to your word vectors if you're familiar with that. So what happens is that we want to transform, say, a single word into a vector form, right? So this vector representation is a learnable representation. There are parameters that basically govern what the vector of a word looks like, and these parameters will be trained during the model training process. Why we call it token is because for transformer models in particular, we very rarely use a tokenization scheme, which is as simple as, oh, let's break up a sequence into individual words. More complex schemes are actually used to break up the sequence into a series of subwords, right? So usually the token is not a full word by itself, but it's a subset of a word. For example, aim could have actually been from a word such as aiming, but then we cut the word aiming into aim and ing, for example, right? So for the sake of being more accurate, we call it token embedding. So these are basically your token vectors, and if you know about word vectors, it's essentially the same idea, right? So what might be a little bit more new to you guys is this positional representation. So here, this is also a series of embedding. However, this is different from the token embedding because for token embedding, we are basically taking every unique word and then assigning it a certain vector. For positional embedding, we are taking a particular position such as 0, right? So 0 would be the first token, and 1 would be the second one, and 2 would be the third one, and so on. So now every single one of this position has a vector that's assigned to it. So this is the embedding for the position. So you might ask how this embedding is actually generated. As it turns out, there are also several ways to do this. The original transformer paper actually used a special sign function to generate the vector for every location. So basically, the position embedding is pre-calculated and then it's fixed, right? So we have a series of fixed embeddings. However, many later models actually make use of learnable embeddings. So what happens is that we treat every position to have a vector that is actually learnable. So same as the token embeddings, this would then be trained as the model is being trained. So the net result is that for every single token inside the sequence, right, the token is itself, and then it also has an associated position, which encodes where it is in the sequence, and then we sum up the token embedding and the positional embedding, and then we get this final input embedding, right? So we can see that when we input a sequence into the transformer itself, we not only encode the token, but we also encode the position inside this singular input embedding. The reason why we need to do this, as you will see later, is because the attention mechanism, that's a key part of the transformer, is actually not positionally aware. However, we know that the order of input tokens, especially in natural language, actually does matter a lot. Hence, we need to, in a way, artificially inject this information and then allow the model to be able to make use of it. Right, so now we'll be talking about the data flow inside the transformer layer itself. At the bottom here, we start off with what we had in the previous slide, which is our input representations. The first step is actually all these input representations as an entire sequence itself is being passed into this multi-head self-attention layer. So we'll look more into this in a while, but for now, let's just focus on what is the output from this layer. The output from the multi-head self-attention layer is actually another series of embeddings, right? So if you imagine the dimensionality of the data at the start and the end is actually the same. And what is curious about the output from this multi-head attention layer is that all these embeddings, right, all these individual embeddings over here, every one of them is actually a combination of the input embeddings. So what do I mean by this? So let's focus on this position over here, right? So this is the second last position. How we get from the input embedding to this sort of intermediate embedding over here is that inside this multi-head self-attention layer, a pairwise score is actually calculated between this position and every other position, right? So you can imagine there's actually a score pairwise between all the positions, and this score is being used to sort of weight how heavily that particular position would contribute to the output embedding over here, right? So every output over here is actually a weighted combination of the entire sequence of tokens. So what this is known as is this is known as a distributed representation, and it's related to the distributional hypothesis in linguistics, right? So you might have heard of it, right? It's a common idea that comes up whenever we talk about word-to-vec. So it's really this idea where a word is characterized by the company it keeps, right? So in our particular case, we are basically treating the sort of the intermediate representation at every location to be a sort of sum of the entire information that is contained inside the sequence, right? So that's the distributional hypothesis, and yeah, it's similar to word-to-vec. So basically, now we have yet another series of embeddings, but at every position, we capture information that is not just in the input embedding at that location, right? So it's the information contained in the input embedding plus the information that is contained elsewhere inside the sequence. So we can see now that actually we are making the representation here more powerful than the input embedding itself. Next, every embedding, we basically do a linear transformation on it. So what we do is that we actually pass it through a feed-forward neural network, and then out comes the output embedding, right? So what's important to note here is that this happens on a position level. So there's no more sort of crosstalk between the different embeddings. We are just transforming every single embedding individually using the same feed-forward neural network. So this feed-forward neural network is usually just two fully connected layers with a ReLU function in between, right? So you can think of it as just a sort of transformation of the intermediate vector here into a output embedding. Yeah. In addition, there's one last feature of this transformer layer that's very important for the data flow, and that is this residual connection over here at the side, right? So the purpose of this residual connection is to allow information to skip past this sort of self-attention layer and also skip past the feed-forward neural network. So what is the purpose of this? There's actually two main reasons. The first one is that the transformer model tends to be very deep, and residual connections are important for training deep models because they allow the gradient information to basically propagate further down the model. The next one is that empirical experiments have found that this connection over here allows important information such as the positional information that is only injected at the very start of the model. So it allows that information to basically be propagated further up the model during the sort of the feed-forward process. So this is also a key feature of the data flow inside the transformer layer itself. So with that, we've covered most of the major operations inside the transformer layer. It's important to note that there are other more minor operations such as the normalization that you can see in this diagram over here. In our diagram, we omit it so that we can see the overall data flow a little bit more clearly. So now let's look at the attention function itself, right? So the attention layer is essentially this function that is presented in diagrammatic form over here and in equation form over here. So what it is essentially a function that takes in three different inputs and produces an output. So these three inputs are known as the Q, K, and V, right? So that's the query, key, and the value. So one way to understand the intuition behind this KQV is to look at the attention function as basically a dictionary, right? So let's look at the query first. So how would we query a dictionary, right? So we have the dictionary, and then we look, and then we say that we want to look for this particular index A. So that's the query. So what is this dictionary, right? The dictionary is made up of the key and the value. So we have the different keys A, B, C, and then we have the values alpha, beta, Charlie. So this makes up the dictionary, and we basically want to query the dictionary. So how the querying process works is that we basically look at the query over here, and then we match it to the key, and then we return the value at that key. So that's our dictionary. Attention actually works in the same way, but it's what we can basically think of as a soft dictionary. So instead of looking for a precise match between the query and the key, we actually allow partial matches, and then how we basically return a value is that we combine all the different values in a dictionary but weighted according to how much the keys actually match the query itself, right? So we can imagine that if I could query something that's between A and B, I would get an output that is a combination of alpha and beta. So this is like somewhat hard to visualize. So I have here a Jupyter notebook that's on Google Colab that hopefully can illustrate the point a lot clearer. Alright, so I encourage you to look at this notebook in your own time if you want to better understand the attention function itself. But what I want to direct you to now is this toy example over here. So for here, we have a sort of a defined query vector, right? So this is our query input to the attention. And we have here a sequence of 5 query vectors, right? So when we pass in a sequence into the attention, we actually have a query key and value for every position inside that sequence, right? So that's what we have over here. We have a sequence of 5 queries, and then at the same time, we have a sequence of 5 keys. So what the attention function will basically do is at every position, match the query to all of the keys and then see how much they match individually and then combine together a result and then return it. So now let's see what happens when we do the attention operation using the query and the key that we defined earlier. So we can visualize the output over here, but let's look at some of the interesting results. So the first one is at the third position, right, where we define our query to be 10, 0, 0. So this is the query vector. The attention operation actually attends this query to this key over here at position 0. So this is actually a perfect score of 1.0 in terms of the similarity. So we see over here the query at position 3 actually matches the key at position 0 with perfect score, right? So that's 1.0. Next, we look at another example to better illustrate the idea of the soft dictionary. So at query 4, we have another vector which is 0, 0, 10, and then we want to match that to the key. But then we realize that the keys at 3 different positions, 2, 3, and 4, actually share the same value. So what actually happens is that at position 4, when we make the query, it's equally matched to 3 different keys. And what happens is that the attention score is essentially divided by 3. So everything here sums up to 1.0, but the score at every location will be 0.333. Yeah. At the same time, you have noticed that for our query and key vectors, we have made them sort of orthogonal. So these are 3D vectors, and every vector here points orthogonally to each other. So they are along the x, y, and z axis, as you can imagine. If we have a vector that's actually not oriented along the axis, but say 555, when we do the attention, it will actually return a partial score for that particular vector because it's no longer a full match. Yeah. So I hope this better illustrates how the attention functioning actually works, and you can feel free to spend more time on this notebook and play a bit more with the values and so on. So now let's return to our presentation over here, right? So we've looked at the attention function itself as a soft dictionary, and let's try to visualize what actually happens inside the transformer. So inside the transformer, we actually call it self-attention, right? So why is this the case? It's because our K, Q, and V vectors are all generated from the same sequence, which is this input sequence over here, and every token is being transformed into a different query key and value vector. Since technically only one sequence is used inside the self-attention, we call it self-attention because essentially it's attending to itself, right? So at every position, a query is generated and then is compared to the key at every other position, and then at the end, the value that's returned is a combination of the value vectors of the entire sequence. Yeah, so we can see this happening over here, right? For example, at this location, we combine together the representations and get the final output representation over here. So what can this attention mechanism actually learn? As it turns out, it's capable of learning very interesting linguistic features. So there's a very nice paper that I've linked to at the bottom over here, where the authors actually looked at the individual attention inside the transformer model itself, and then actually went to interpret what every attention head is actually doing. So we see over here there's an attention head that actually learns positional information. So basically it learns how to relate one word to the previous word in the sequence, right? So we know that that's generally how a language works, right? When we read a sentence in a sort of sequential order. And next we have this syntax that is learning. So it has learned that there needs to be an agreement between a pronoun and a verb. And the last one is that we have this special head over here that is learning how to basically highlight rare information. So in this case, whenever there's a rare word, the entire sequence will attend to the rare word. So of course, every attention mechanism can only learn one particular variant of feature, for example. So this is not unlike your convolutional neural net, where one filter learns to extract a different feature, right? So how do we overcome this barrier? Of course, we can have multiple attention that we put into the model. However, that is very computationally inefficient. So what we do in practice is we have this idea of a multi-head attention, where the idea of these multiple heads is to specifically split up the input into the attention operation along the embedding dimension, and every head will basically work on a subset of the input. What we see over here is an exploded view of the input into the attention, into the multi-head attention, right? So the input has a dimensionality of your embedding dimension times your sequence length. So every column over here represents the single embedding that is generated at that position in the sequence. What we do is that we divide this along the embedding dimension, right? So we retain the entire sequence length, but we carve out one portion of the embedding at every position, and then we pass that into the attention head. So for this example over here, our embedding dimension is 8, and we have 4 attention heads. So every attention head works on a subset of the original embedding with only 2 dimensions. So this is a diagrammatic form of what I've talked about earlier. So for this input sequence over here, we basically do a linear transformation and create separate query and key vectors, and then the original vector is usually retained as the value, and then we perform the attention operation, and then at the very end the attention head returns the final output, which is the sort of combined value vector. So that was attention, right? We've talked about this basic form of attention, which is actually found in the encoder part of the transformer network itself, right? So that is known as the bidirectional self-attention, or the encoder style self-attention, right? Because at every position, you are allowed to attend both forward and backwards, right? So that's the animation that we saw over here. At every position, we can attend both to vectors on the left and on the right. There's actually a different style of attention known as the decoder style attention, also known as the autoregressive self-attention, right? So what actually happens here is that the the token at every position is only allowed to attend to previous tokens. So for example, at this starting position over here, it can only attend to itself. At the second position, it can only attend to the first position, but it cannot attend to the second position over here. And the second position can basically attend to everything else. So this basically is a limitation that is added into the attention mechanism so that certain blocks are not allowed to be attended to, right? So the attention weights for those are forcefully set to 0. You can look at it that way. And since in our transformer model, there's both an encoder and a decoder, we have the encoder portion that individually uses the bidirectional self-attention. We have the decoder portion that basically uses the decoder style of the self-attention. And then in between, we actually also allow the decoder to attend to the outputs of the encoder, right? So there's this sort of third variant of the attention, where this is still self-attention, but we're basically attending to a different set of the we're attending to a different set of input representations. So that's actually what you see over here, right? There's actually 2 different inputs into the decoder block, and we need to attend between both of these inputs. So there's that third variant of attention. And you can see that actually over here, this shows the difference between the encoder block and the decoder block, right? The encoder block was the one that we did a deep dive into. So there's the attention, the multi-head attention, and then the feed-forward network. For the decoder portion, there is the same thing, where it works on the input into the decoder block, but then after that we have another multi-head attention layer that works on the output from the first attention layer, and then the output from the encoder block itself. So the decoder block has 2 of this attention. There's also a different variation of the transformer network. So this is actually a lot more popular now. Is that we only use one half of the transformer model itself. So the first one that we're going to look at is the decoder only model, right? So this model over here only has decoder blocks, and since there is no encoder block over here, we have we no need to include the second attention multi-head attention layer inside the transformer block itself. So what we basically retain is basically the decoder style of self-attention, and then we have a series of transformer blocks or transformer layers that apply the decoder style. So as it turns out, this decoder variant of the transformer model is actually very good at generating text and is basically used as the architecture in models such as GPT-2 from OpenAI and Megatron from NVIDIA and Control from Salesforce and so on. So all of these are actually very powerful text generating models. Next is the encoder only version of the transformer. So basically all these are the encoder blocks like what we have seen in the presentation, and all of these use the bidirectional variant of the self-attention. Right, so this variant of the transformer has shown to be extremely good at feature extraction and therefore achieves very high performance when we fine-tune this on downstream tasks like question answering and so on. So this is the variant of the transformer that is used in BERT, as well as the other variants of BERT like Roberta and Albert and so on.